Welcome back. Today for our first lecture, we have Elena Guardo from the University of Catania. She's going to continue the mini course on points in projective space.
Okay, hello everyone. Thanks for coming. And also a special thank to all the organizers, in particular to Adam, that involved me in this experience. Okay, thank you, and I'll try to start. Okay, just few. I apologize for my Italian English, but I'll try to be understandable as much as I can. So I'm going to talk about fat points. That is a special schemes in geometry, but I don't want to bother you much with geometry. So you just think about special set of points where we put some special multiplicities to these points. Of course, what we want to know is the Hilbert function. Of course, the Grady-Betty numbers, but it's step by step. But it's not so easy. I can try to show you some easy examples where you can see that there is really a difference. It's not, there are still a lot of unanswered questions. And this is also the reason why I'm talking about fat points in P2, to make easier the problems that I want to show you, not because we cannot define. We can define fat points in Pn, but then the problem is to study this set of points. They are very strange even for 2 points on a line, I will show you later. And then the direction is, since much, we can have 2 directions, because we have a set of points, I'll use my hand, sorry. We have a set of points, and then we put some multiplicity. So these points can be spread in a many different ways in the plane. So the geometry of what we call the support is much affect the result on the Hilbert function. So there is one direction that we are talking about fat points, general collection of fat points, and then we can restrict the attention to the support, so some special support, since as Adam said, for reducing set of points, we know everything. Then we know also the geometry and any invariance or homological invariance. So we know the geometry on the support, and it will help us to understand what about the set of fat points. But when we restrict the attention to the support, we also restrict the number of points. And I'll try to be as much as can clear to understand this. So let's start. I will repeat some definition that you already know, and but try to not overlap. Okay, still, so I'm going. Points in P2. So still K is an algebraically closed field of characteristic 0. And we are going to use R, the usual polynomial ring, in 3 variables. I'm not going to use Yx, so maybe for some example. So this is my polynomial ring. And then let's consider X a set of points. Okay, let's say reduce it. When means that all the points are distinct, okay? Reduce a set of points in P2, and then maybe from this line horn, and take some, let's say, non-negative integers, but of course we need that they are every bigger than 0. Integers. Okay. Then we define this set of fat points. Okay, we denote M1 P1 plus MS PS. So this is the scheme. I think that the people don't, it's the right size, right? And the defining ideal, it's defining ideal is I of z that is given by the intersection of the ideal of the points. So the another notation is also this one. Where Pi is the prime ideal associate to the point Pi. We call it set. Z is a set of points that most of the time, maybe it's usual for me to say third point schemes. You don't have to care about schemes. Just set that it's a set of points whose support on X. So this is why in the introduction I said that X has an importance in the study this scheme. So we are interested to know what we can ask which is the Hilbert function of Z first, right? So, for example, let's take an easy example. I know that it's easy, but just to understand. Okay, Adam introduced the ideal points and then take 1 point. So 1 point, the ideal in P2 is generated by 2 linear forms. Okay, if you just want to make an example X and Y, but doesn't matter. So if I want to take, for example, the multiplicity M is equal to 2, then I'm asking who is this third point, the set of double points, or just 1 point, okay, double. So it's just L1 square, L1, L2, L2 square. Just make the power, okay? Okay, this is also, okay, now, if we want to compute the Hilbert function of this guy, remember that we are working with the Hilbert function. I'm just remember the Hilbert function of the module in degree T is given by the dimension of our polynomial ring in degree D that we can see as a vector space. So it's equivalent that we are counting all the curves of degree D in P2 in this case, T, sorry, minus the dimension, okay, in K of the ideal in degree T. So each piece is graded, and you can look at them as vector spaces. So we are trying to understand which is the dimension of all the curves in degree T, that in P2 it's T plus 2 choose 2. This is the number of the curves in degree 2 in P2, minus the dimension of this ideal, okay? So our problem is to understand how we can compute this. So for 1 point, it's one simple point, which is the Hilbert function. So if we want, if X is the point P, which is the Hilbert function of X, Okay, just be careful. Every time I say Hilbert function, something, I'm referring to the module, because there are in the literature some authors that consider Hilbert function of the ideal. So be careful when you read the paper, that if they are referring to the Hilbert function of the module, that is this one, or just the Hilbert function of the ideal, that is just the dimension of the ideal. Okay, so I'm always referring to this one. So in case we have a point, so in degree 0, by definition, is 1. In degree 1, so we are asking, how many lines contain 1 point? Of course, we have 1 point, and as Federico, you said something about Hilbert polynomial. Then on certain points is the degree of the scheme. So recalling that 2 days ago, Adam talked about the O sequence, right? In the special case where we have points, then the sequence, O sequence of a points, then when it reaches the degree of the set of points, then it stops. So it goes to the degree always at the same time. Once we have 1, we have 1 point, the degree of a set of points with 1 point is just 1, so it goes 1 forever. Okay? In case we have Z, that is our points and the square, then we have 1, that is the Hilbert function, okay? In degree 1, how many lines? Of course, we have just already reached the degree of the scheme. So here we have 3. So it's just, so the dimension is because a line is something that is as degree 1 and the point something is in 2. So by Bezout theorem, there should be connecting 2 in 2 degrees, so just nothing. So the ideal is empty. One more thing so that I forgot here, we have that the degree of the scheme Z is equal to the sum for S of the degree of each point. Each point, so for example, each point of multiplicity 2, the degree of a point of multiplicity 2, let's say in this way, so it's 2 plus 1 choose 2, right? So it's 3 choose 2 is 3. So this means that a 5 points of multiplicity 2 is equivalent to a scheme, a set of points of degree 3. So this means that the Hilbert function will stop at 3. So this is the degree of the scheme. So once we get 3, then we also have 3. Okay, let's go. Let's recall. So in computing the Hilbert function, so when we compute the Hilbert function, let's say HF of Z, we are looking at the dimension of the ideal in degree T. So we call this number what is the actual dimension of Z. In particular, you can, in the literature, this is equal to the dimension. So what we are looking at some curves that pass through the points with a certain multiplicity, mi, right? So in the literature, It's called the dimension of the system of the curves of degree T vanishing, okay, vanishing at each point pi with order, let's say, multiplicity. At least, let's say, mi. So this is the actual dimension. And we also recall that the polynomial, the Hilbert polynomial, or maybe, so recall what Fred said, that the Hilbert polynomial is this property, okay, just recalling the property, okay, is such that for T bigger enough, then we have that the polynomial of Z, the Hilbert polynomial of Z is equal to the degree of Z, okay? So as I said before, so in our case, then we have the degree is just the sum of and we define this number, what is called the virtual dimension of Z, that is, so the virtual dimension of Z, that is this number. It's equal to the dimension of our, let's say T, I use T, minus just want to say the virtual, okay, minus the Hilbert polynomial of Z. I put one plus because this number can be negative, okay? So this is, in our case, equal to the dimension of the ring in degree T minus the sum for E goes 1s of mi plus 1 choose 2. This is the virtual dimension. So it can happen that when the actual dimension is equal to the virtual dimension, then we say that the system is regular, but think that we can, in this context, we can say the linear system is regular. Is regular or not special. And this is not special. But as I told you before, this plus means, so when we say x plus, it means that is or 0, okay, if it's negative, or x if x bigger equal, just 0, and that is otherwise. Should be positive, otherwise. Otherwise, what does it mean? As I told you before, the actual dimension is, so this is can be negative, so in general, otherwise is not, special. Special or superabbondante. Roughly speaking, we have something that is a curve unexpected. Because the actual dimension can be equal to the virtual dimension plus something with, that is bigger than a number, let's say. So this is S is just the superabundance. Yes.
In the definition of virtual dimension, is there a T somewhere, or like, I'm just saying the left-hand side doesn't depend on T.
Because we are looking the virtual dimension essentially in I of Z in degree T, let's say in this way. Because you look in this context, you just look at the piece of the dimension.
Yeah, and quickly
the Hilbert polynomial, that is the degree of Z, so this is the one, okay?
The actual dimension be equal to the virtual dimension for every T, for it to be regular, or
no, in that piece, in degree T. In degree T, because we are looking at the curves in degree T. We are looking, each time that you look at the Hilbert function, you are looking at the graded piece in degree T. I'll show you with an example next. So you are asking if the linear system of the curves of degree T. So every time for each T, you can ask if you have curves or not. Let's show you an example. For example, take two double points. And then we want to compute the Hilbert function of this guy, okay? We want to compute the Hilbert function. So our Z is 2p1 plus 2p2. My support is X, that is just two collinear points, okay? And we know everything for when mi is equal to 1. So let's compute this Hilbert function. We can do this together. Okay, in degree 0 is 1 by definition. In degree 1, is there any line that contains these 2 points with multiplicity 2? You can just think Bezout. I mean, Bezout theorem just say that 2 reducible curves in degree d1, d2, they intersect exactly d1 times d2 points. So this, roughly speaking, this is Bezout theorem. So a line intersected this scheme in something where the multiplicity, the intersection multiplicity is 4, no? The sum is 4. So of course there is no any line contains this. So if you remember, the Hilbert function is the dimension of R in degree 1. Well, okay, that is T, so 1 plus 2, choose 2, that is 3, minus the dimension of the ideal, so we didn't find any lines, so here we have 3, okay? So I'm just computing this number here. The number T is equal to 1, so we have 1 plus 2, choose 2, minus 0. So it's just 3, okay? So let's go in degree 2. So how many conics pass through this scheme? a conic is a curve degree 2. Intersect the line, they should be contains, okay, so it's the conics will be reducible, so the conics split on a line and another line, so the conics should there is the conic that is just this line times something with degree 1 1, okay. So the line, there is a line passing through these points, of course, so the conic is just, if we call by abuse of notation L, okay, because it's just the line of the square. So this is the conic. So if we have the conic, so let's compute the Hilbert function. So for t is equal to 2, we have that the conics in degree 2 are exactly 6 because it's the binomial coefficient, minus 1 that it is the conic. So the dimension of the ideal in degree 2 is 1 because it's just the conic. So here we have 5. And then since the degree of our z is just 3 plus 3 because it's just the sum of the degree of each double points. So this 6, then by properties, I don't want to take more time because it's almost done. So it's 6. This is reach the degree of the scheme. But I want to say something. Here we got that here is, we have something here, but if we compute the virtual dimension, so if we compute the virtual dimension, if we compute the virtual dimension in degree 2, this is equal to t plus 2, so it's 2 plus 2 minus the sum of, for e is equal to 1, of 2 plus 2 choose 2, right? Sorry, double points. This is the degree of the so this is 6 minus 3 minus 3, so it's 6, so it's 6. So what we have, that in this case, we have something that is unexpected. We would expect 0, but the actual dimension, so the dimension is 1, the dimension of height z in degree 2 is 1. So this is the actual, what I call the actual dimension. So it's equal to 1 plus 0, right? Okay. So this 0, this is the virtual dimension, and 1 is the sobreabundance. So, and this is the first easy case where the things doesn't work, because for reducing points, everything is nice and so. So this is the first, let's say, easy case where working with double points is not so easy as we expected. And there is the main theorem that about general collection of fat points is from Alexander Ischwitz theorem. Do you have the time to state it? Otherwise I will. So, 2 minutes, okay. So the easy case where we can see unexpected behavior of fat points. Because we would say that the Hilbert function or like of a scheme of degree 6, like 6 generic points, and that this is not true. So the Alexander Ischwitz theorem so This is from Alexander Ischwitz. Okay, let X be a collection of S general points in, it says in Pn, so this is a special case, where case our closed characteristic 0. And let's say, try to be shorter as fast as I can. So let X be the in RD, the subspace of polynomials of degree D through my English for X with all first partial derivatives vanishing at the points of X, then this then I of X of D as the expected dimension except, so this is the minimum between n plus 1 times S and the binomial coefficient. Except in these cases. Except. Sorry. Okay, first case is D, so conics, in case where we have as the number of points is between 2 and n. Then we have, this is the case that I've shown you now. So in P2, we also have the quartics through 5 points. In P3, we have the quartics through 9 points. In P4, we have cubics through 7 points. And in P4, the quartics through 14 points. As reference, we have all the Alexander Ischwitz paper, but there is a nice paper from Brambilla Ottaviani. Brambilla Ottaviani. So, sorry, I took 3. The things will be worse in P1 cross P1.
All right, maybe time for one quick question. Any question? I actually have just a clarification. So to ask that the first partial derivatives vanish means we're looking at double points, right?
Double points.
Okay. So
yes, all double points here.
Okay.
This is the reason why. But then there are other. So for collection of general points, we have resulted until m smaller or equal than 20. So it's still open problems. So. of course, if we restrict the support, I mean, we are just taking points on a line, so it's easy. But even for this case, we have something different.
All right.
Anyway, I will put the notes in the web.
Okay. If there are no other questions, then we can thank Elena again.